All right, folks. Well, now that we've talked a little bit about attributes and binding, and we've talked about types and type checking, I want to spend a week or so going through a whole slew of different specific data types and just looking at implementation issues with them, looking at the properties we want to associate with that data type, looking at storage mechanisms, looking at the common operations that we might want to associate with that data type. And so we're just going to cover a whole slew of these. And what I'm going to do is start off with the sort of simple primitive data types, and then we'll start looking at some of the more advanced and or some of the composite data types and whatnot in our future sessions. So there is the plan. Let's see what we can have a look at. Obviously, as a programmer, we want to know what kinds of data we can model easily in any given language. And for each of the different data types that we can work with, we want to look at what kind of operations are supported for that data type. Right? Anything that's built in, we can make use of directly. Anything else, we either have to find a library for it or we have to write code for it ourselves. Obviously, we're interested in the syntax and the operations for each of the different data types. We want to know a little bit about the internal representation for it. And we're going to wind up looking at some of the issues in sort of specialty languages, right? There's a lot of common data types that are supported for almost all languages, but there are always a few languages that have a kind of a bit of a niche approach to things. So things like strings in Bash, right? Where you assume that since we're focused on a command-driven language, we're going to assume that pretty much everything is a typed command of some form, then we'll pretty much treat it all as strings. And where we need to, we'll convert it into other stuff. So the first thing I want to look at are the primitive data types, the sort of core data types that aren't a collection of other things. So this might be things like our integers or our floats or our characters, things like that. They're really simple basic types. And then we'll get into looking at the composite types where you're talking about something as a collection of these. So the idea of a record or a structure where you've got a bunch of different fields, or where you're looking at an array, or whether you're looking at a vector or whatever it might be, some kind of composition that's a whole bunch of the primitive types glued together. And then we'll get into the discussion of user-defined types. Right? In the language, is it possible for the programmer to go through and define their own new data types as some composition of other things? So we'll focus on the primitive types for now. And again, the typical ones are integers, real numbers, characters, and Booleans. Right? For each of those, you might have a variety of kind of different flavors of them. So if you think of integers, you might have integer representations that are just 1 byte long or 2 bytes long or 4 bytes long or 8 bytes long. And, the idea of a short or an int or a long or whatever it might be. And similar ideas for reals. If we look at something like C where we've got floats and doubles and whatnot, you've just got collections that are essentially the same type of data from an abstract point of view, and they're using similar representations. It's just they've got different amounts of storage space associated with them. Right? Characters, again, you might have one set of characters that are, or one character type that's just, let's say, for ASCII characters, and you might have another one for Unicode characters. But again, typically you're looking at these as relatively simple data types. Booleans, true, false, again, might be theoretically could represent as a single bit, but typically represented as a byte. Again, the small data types are simple primitive data types. We'll also talk about the ordinal types, where usually these are kind of a simple variant on our primitives here. So these might be just a subrange of the characters, or a subrange of the integers, or a subset of the characters or integers, or a bunch of enumerated values. So we'll look at the ordinals. We'll look at strings, and strings is kind of an iffy one. Quite often they're represented as something like an array or a vector of characters. So we'll treat these as kind of our borderline as we make the transition from primitive types to the composite types. So start off with the integers. Again, typically the integer data type or types for any given language will use a fixed storage size, and you've got some fixed range. So maybe for unsigned integers, you've got 0 to 65,000-ish, or for signed integers, you've got negative 32,000 and whatever to positive 32,000 and whatever, just based on the kind of 2's complement representation and however many bits you've got set aside as storage for that data type. Right? So whether you're talking about a 16-bit or 32-bit or 64 bits, right, it's just going to determine what fixed range of values you have available for that integer data type. And again, usually there's a kind of typical fixed set of arithmetic operations, addition and subtraction and division and modulo and whatnot. Those are often pretty closely tied to the hardware support for integer operations. And again, those might include things like bit shifts and bitwise operators for ands and ors and exclusive ors and nots and all that kind of idea. There's often going to be some kind of implicit conversion supported for conversions to and from reals, right? All the time we're writing expressions that use a mix of ints and reals. And so those are pretty commonly supported operations. And again, depending on the language, it might also provide direct support for conversions to and from strings, just because quite often you're going to get the user to enter something as a string and then store it as an enter the string 327 and then convert that to the integer 327. So again, the representations behind the scenes we should be pretty familiar with by now. And typically, if we're looking at 2's complement representation, then we're looking at negative 2 to the n minus 1 to positive 2 to the n minus 1 minus 1. Or if we're looking at unsigned, then it's just 0 to the 2 to the n minus 1. Now, your compiler, when it's going through looking at your code, might do some tweaking to whatever it is you've represented. So the operations that you put in your source code might not be what the compiler eventually winds up carrying out. If you do something like use the expression 16 times x, where x is an integer, then the compiler might recognize, oh, you know what, I can do that a lot. Multiplication can be kind of slow and expensive. If you've got a power of 2 that you're multiplying by, then I can do that a lot more effectively just using bit shifts. So I might shift x left 4 bits instead. Or it might look at some combination of operations that lets it do things more efficiently. So if you do something like, say, x is assigned 37.5, what the compiler might wind up doing is saying, well, I'm going to find the integer whose bit pattern is the same as the bit pattern for the float 37.5, and I'm going to store that integer bit pattern, and when I initialize x, I'm actually going to do the int operation rather than the float operation. So there's all sorts of little tweaks that the compiler might be carrying out behind the scenes to make things run more effectively during execution and have, as far as the programmer is concerned, the same visible effect. And obviously, in addition to the integers, we typically have some version of real numbers supported in most languages. And again, there's all sorts of typical representations, whether it's 2's complement or whether it's sort of a sign magnitude approach. But you are, again, going to have, pardon me, not 2's complement for real numbers, but some form of representation where you might represent a sign, you might have a fixed number of bits for the exponent that you're trying to multiply by, and a fixed number of bits for the precision that you're working with. All right, so you might decide that, okay, if we're going to represent 34.75, then if I was thinking of it just in terms of a binary representation, right, that could be 32 plus 2 plus 0.5 plus 0.25. So as a bit pattern, kind of in an abstract idea, this would be our 1, 0, 0, blah, 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 blah. Right? Just look at the again, thinking of each bit representing 2 to the whatever, or 2 to the negative whatever. Right? We could think of this as the natural bit pattern, if you like. But in fact, the typical representation is going to be something more like, well, let's represent it with the decimal point in a fixed location. So we'll just shift everything to have the decimal point in a fixed location, 1 point, blah, 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 blah. And we just shifted everything over. And then we're going to multiply that by 2 to the 5. So in terms of the internal representation, we might have a 0 bit to indicate that this thing's positive. We'd have this sequence of bits to represent the actual value, and then however much we needed to shift it by. So again, you might have 1 bit for the sign, 4 for the exponent, 11 for the mantissa, or whatever it happens to be, and you get the internal representation that you're targeting. Actually, a pretty common simplification is to say, well, whenever we do this shift, we know that that bit on the left-hand side of the decimal point is always a 1, so we don't actually have to store that. So you can actually get one hidden bit of our representation by saying, okay, there's an implicit 1 there, and then we'll store the rest. However, again, in terms of the operations, you've usually got some host of math operations available to you. Sometimes there's a floating point unit to take care of that. Sometimes we'll carry out operations in software. Typically, they're more expensive operations than our integer operations. So where possible, you're going to carry things out as integer operations. But again, the real number math is obviously something, floating point math is something that we're obviously going to deal with a lot in most programs. And it's the compiler's responsibility for the most part to figure out how to come up with an effective implementation of the floating point expressions that you come up with as a programmer. Now, there are a few other numeric data types, right? We've got rationals where we've got, some integer over some integer. So it's pretty common if a language does have a rational data type set aside for it to actually represent it as 2 integers, one for the numerator, one for the denominator. And again, the usual collection of math operations. There are a few things to think about in terms of how this is going to get stored. Does this automatically carry out simplification? If I've got 2 over 2, does it actually store it as 2 over 2, or does it actually store it as 1 over 1, or what's the idea? But and our usual error handling in terms of, oh geez, what if the denominator is a 0? What happens then? Things like complex numbers, where you might have, again, storage for the real and the imaginary component for it, and some kind of decision as to what sort of software operations are provided as part of the language to work on those complex numbers. Now, if we've got this idea of fixed-sized integers, and again, maybe shorts and longs and ints and whatever else you might have, or fixed-size reals, floats and doubles, what do I do if I've got numbers that are bigger than that? What if I actually want to store something as an integer with all of its precision, right, all of its digits, but it's too big to fit in whatever my biggest sized fixed integer is? So some data types provide something like a big num idea, an arbitrary, where you can hold arbitrarily large integers. And here, this is again drifting more into the composite data types, where what this might actually represent it as is something like a linked list of integers or an array of integers, where it represents the number in chunks and then provides some kind of software support for operations on those big integers or on those big floats or whatever you want to call them. Booleans are again supported by most languages as a data type, again where you've got some kind of representation of true and false. There's often a tie to some underlying data meaning. So in C, you've got this notion that 0 is false and anything else is true. In Lisp, you've got the idea that nil is false and anything else is true. So you do want to be aware as a developer what the kind of true operations are on your Booleans. So if I say something is, if I assume that something has to be equal to 1 for it to be true, that's not quite going to match with the way things are actually done in C. Or if I assume that in Lisp something has to be equal to t to be true, that's not necessarily going to be quite the case. Right? This idea that if it's not 0, it's also true, even if it isn't 1. So typical operations for Booleans, assignments, inequality tests, and or not. There's often support to be able to go back and forth between whatever the underlying type is and your Boolean type. So your Booleans might actually get represented using 0 for false and 1 for true, with again the underlying notion that in fact anything that's not 0 is treated as true. But that usually provides you with a way to do a conversion between, say, integers and Booleans. So you do want to be aware of what implicit type conversions are supported and how that's tied to the underlying implementation of the data type itself. And again, theoretically, a Boolean could be represented as a single bit, but in fact, usually your smallest addressable unit is a byte of some form, so that's more commonly the implementation. Characters, obviously we want to be aware of what character set is in use. Is it ASCII? Is it EBCDIC? Is it Unicode? Are there fixed sized character representations or variable size? So if you've got Unicode representations, does it assume that it's always 8 bytes, or does it actually allow for flexible Unicode byte sizes for our characters? We want to know what the syntax is for referring to a char. Right? Obviously, we've seen the kind of single quoted version in something like C, or now we've seen the hash / whatever it is in something like Lisp. Obviously, you've got operations in terms of assignment and equality tests. If you've got 2 character variables, are they the same? Do they have the same content? Do they have different content? Can I copy from one to the other? Quite often, we've got operations for testing certain properties. Is it a digit? Is it an alphabetic character? Is it an uppercase? Is it a space? Is it a punctuation? That sort of idea. Maybe conversions related to that, convert to uppercase, convert to lowercase. Maybe translations between the underlying implementation and the character that we're interested in. So if the underlying implementation is as an integer for ASCII or for some byte sequence for Unicode, can I go through and convert between some character and the integer representation for it? There might be operations that allow you to do some comparisons on ordering, in which case you have to be aware of what ordering it's actually using. So if I compare character X and character 3, which one is less than or greater than? So quite often, behind the scenes, that's just based on whatever the implementation they're using for these. So if you've got your characters represented as ASCII codes, then it's just going to say, okay, which one's ASCII code is bigger? Or similar idea for, if it's represented as Unicode, which one's got the bigger Unicode value? So you do need to be aware of what the underlying ordering is when it's doing comparisons. So in terms of data types and implementations, just to take a look at a couple of sort of supporting things that are often given to us. Languages like C or C++ allow us to go through and find out how much storage space is allocated for an item of any given type. So you can specify what data type you're interested in and use the size of operator. And this is going to tell us, okay, a short takes up however many bytes, an int takes up however many bytes, a char takes up however many bytes. And this works on user-defined types as well when we get there. So if you often create a struct and say, well, how many bytes does that struct take up? It'll go through, and the size of operator will figure it out and tell you. Right? Because obviously the compiler knows how many bytes are supposed to be allocated to each of these things. Now, one of the things that we'll play with a bit over the course of the term is looking at the internal structure of data types. And this gets more interesting as we look into our composite types, but even with things like our floats, it's interesting to see what the internal structure, what the byte patterns for our floats happens to be. If we start looking at some of our composite types, and let's say we look at something like a struct that we went through and created here, where we've got an int field and a float field, it might be interesting to be able to look at, find the memory address for my variable of this struct type and figure out where the int field is and where the float field is. Right? So we can go through and do things like grab the memory addresses for different fields, right? I can grab the memory address for my struct as a whole, grab the memory address for the first field, grab the memory address for the second field, and figure out where these things are stored. And again, as we come back and look at implementation issues, we'll find all sorts of interesting things there. And then we'll look at the idea of, particularly in C, where we can use all sorts of weird and wonderful magic to get at the internal representation of things. We'll take a look at how we can use typecasting to go through and look at the actual bit patterns that are used to store different things. So if I've got a variable of type, whatever it happens to be, can I go through and actually look at where this thing is stored in memory and look at the bit sequence that's actually stored there and see how these things are being represented. So we'll play with that to examine the internal structure of different data types. Just from a pragmatic point of view, let's see if we can go through and reverse engineer things, if you like, and find out how things are actually stored. And so between these, we can go through and use our C to play with the internal structure of a lot of different data types. And that's something that we'll play with as we go through here. So just to kind of do a little bit of foreshadowing before we get into our composite types here, let's say I do something like create a struct type that's got an integer field and a float field. And then I'm going to use a union to go through and say, let's come up with a little cheat type here where we say my union can be either one of these structs or it can be a pointer. And then I'll create something of this cheat type, and I'll assign fields to it as if it was a struct. And then after I've done that, I'll go through and say, okay, now let's go through and treat it as our pointer type and look at the data as a pointer, and I can actually look at the memory content of this item based on that. So I can go through and figure out, so when I went through and put a 25 into my struct int field and a 5.375 into my float field, where did that wind up in terms of the bit sequence? So if I go through and then look at the implementation of this, I can take a look at where the 5.375 wound up and where the 25 wound up and see how it actually stored this as a bit pattern. However, that's the kind of thing that we'll play with as we go through to start exploring how things get implemented. You know, we've got our nice high-level view of the world where we think of what our struct has in it abstractly. What does that really look like in terms of the underlying implementation? Once the compiler gets done with it, what does that become? So those are some of the things that I want to play with over the course of the term. All right, that's a good place to leave it for now, and we'll come back and start looking at more and more data types over the next week or so.